Welcome to our quantum deep dive. Today, we're jumping into one of the most game-changing discoveries ever, nuclear fission. And we're going to unpack this whole story of surprise, genius, and a power that literally reshaped our world, all based on a fantastic essay by Jörg O. Schnippet. Okay, so let's set the scene. Picture it. It's December 1938, a lab in Berlin. Europe is teetering on the edge of war, but inside, a totally different kind of drama is playing out. What they stumbled upon wasn't some planned invention. No, it was a massive, world-altering accident that took the entire physics community by complete and utter surprise.
This thing was so new, so out of left field, it didn't even have a name. It was the brilliant physicist Lise Meitner, who, by the way, had just escaped from Nazi Germany, and her nephew Otto Frisch, who finally gave it one. They called it fission, borrowing the term from biology, because it was like watching an atom do the impossible, split in two, just like a living cell.
And that brings us right to the heart of the mystery that two chemists, Otto Hahn and Fritz Strassmann, were facing. They were doing what seemed like a straightforward experiment. They were shooting neutrons at uranium, which was the heaviest element anyone knew of back then. The goal? To create even heavier elements. Transuranic elements. It was the logical next step.
But instead of something heavier, what they found was barium. Now, you have to understand, at the time, this was just impossible. Barium's atomic number is 56. Uranium's is 92. Finding barium was like, throwing a bowling ball at a wall and having it turn into two baseballs. It just completely flew in the face of everything they thought they knew about nuclear physics.
But here's the thing. An accident like this doesn't just happen in a vacuum. It was really the wild conclusion to decades of these incredibly rapid discoveries that were completely rewriting our rulebook for the atom. Think of it like a giant puzzle, and scientists had been finding the pieces one by one, leading right up to this moment.
And you can see how fast it happened. In 1897, J.J. Thomson discovers the electron. Boom, the atom isn't indivisible. Then, 1911, Rutherford's gold foil experiment shows us the tiny, dense nucleus at the center. Just 2 years later, Niels Bohr drops quantum theory into the mix to explain electrons. But the absolute final, crucial piece of this puzzle clicks into place in 1932 when James Chadwick discovers the neutron.
So, why was the neutron such a big deal? Well, because it was basically a secret agent. It could go where other particles just couldn't. See, if you try to poke at the nucleus with a positively charged proton, it gets pushed away by the nucleus's own positive charge. It's like trying to push two powerful magnets together. But the neutron? It has no charge. It's neutral. So it could just sail right past the atom's defenses and get into the nucleus. It was the perfect little projectile to find out what was really going on in there.
So let's go back to that lab in Berlin. Hahn and Strassmann are staring at their impossible result, barium. So what do? They write a letter to their old friend and colleague, Lise Meitner, who's now in exile in Sweden. And it was Meitner, looking at their data from hundreds of miles away, who had the aha moment. She's the one who put all the pieces together and came up with a radical theory for what was actually happening. What Meitner figured out was that the uranium nucleus wasn't just getting chipped, it was being violently torn apart. And the incredible amount of energy being released, it all came down to a few core ideas. First, when you added up the mass of the pieces left over, like barium and krypton, it was just a tiny bit less than the mass of the original uranium atom. This missing mass, or mass defect, wasn't gone. It was converted directly into pure energy, just like Einstein's famous E=mc² formula had predicted decades earlier. And we are talking about a staggering amount of energy, about 200 mega-electron volts from a single atom splitting. To give you some perspective, that's millions of times more energy than you get from a typical chemical reaction, like burning a piece of coal. The scientists knew, right then and there, that this wasn't just some new reaction. This was a new source of power on a scale humanity had never, ever seen before.
But there was another piece of the puzzle, and this one was maybe even more important. When that uranium atom split, it didn't just release a ton of energy, it also shot out 2 or 3 brand new neutrons. And what could those neutrons do? Well, they could fly off and split other uranium atoms, which would release more neutrons, and on and on and on. This was the real secret. This was the key to unlocking all that power, the chain reaction. Now, this idea of a chain reaction immediately led scientists down 2 very, very different roads. The first was a path of control. In 1942, a team led by Enrico Fermi in Chicago built the world's first nuclear reactor. They They figured out that by using materials to basically soak up the extra neutrons, they can make sure that exactly one neutron from each fission went on to cause another one. This created a perfectly stable, self-sustaining reaction that gives off a steady flow of energy. And that's the basic principle behind every single nuclear power plant operating today.
And then there's the other path, the uncontrolled one. If you get enough of this fissile material together, what's called a critical mass, and you don't do anything to absorb those extra neutrons, well, then the reaction just runs away with itself. The number of fissions grows exponentially. One split becomes 2, 2 becomes 4, 4 becomes 8, 16, all in a tiny fraction of a second. The result is a catastrophic, explosive release of almost all that energy at once. And this, of course, was the terrible principle behind the Manhattan Project and the atomic bombs.
So you hear that dramatic history. Nuclear power plants on one hand, terrifying weapons on the other, and you might think, okay, the story of nuclear fission is pretty much done. It's written. But the truth is, it's actually just starting a brand new chapter. This 80-year-old discovery is being completely reimagined for the 21st century. Yeah, it really makes you ask, is that it? Is fission's story just about making electricity and building bombs? Or is there something more? It turns out scientists today are finding a surprisingly new life for this old discovery, and it has everything to do with the cutting-edge world of quantum technology.
This is a really fundamental shift in how we think about it. Back in the 20th century, fission was the technology. It was the end product. You split atoms to get energy or an explosion. But today, fission is becoming a tool for other technologies. It's not the destination anymore. It's the vehicle that's taking us to a whole new wave of quantum discoveries.
It's kind of amazing, really. The story has almost come full circle. Those very same neutrons that caused the fission reaction are now being used as super precise probes. We're using research reactors to create powerful beams of neutrons that let scientists study the bizarre quantum properties of new materials. And in this really cool twist, scientists are now trying to build quantum computers powerful enough to simulate fission itself. If we can do that, it could help us design much safer and more efficient reactors for the future.
And you can see just how much things have changed. I mean, sure, energy and medicine are still a huge part of the picture, but look at this. Fundamental quantum research now makes up the biggest piece of the pie. The discovery is literally feeding back into the science that created it, and it's pushing the boundaries of what we even know about the quantum world.
So when you just step back and look at the whole arc, it's just an incredible journey, isn't it? It starts as a weird result in the chemistry lab, becomes a force that defines global politics for half a century, and now it's become a key tool in our mission to build the next generation of computers. It's such a powerful example of how fundamental science works.
You can really see that evolution right here. The main focus of nuclear science has just changed so dramatically. In the 1940s, the entire goal was just, can we make a chain reaction happen? By the 70s, it was all about building massive power plants. And today, a huge part of the focus is on using fission to unlock the next great technological revolution, quantum computing.
And that's really the big lesson here, right? When Hahn, Strassmann, and Meitner were scratching their heads over those bizarre results back in 1938, there is no way they could have dreamed that their work would one day help us design things like superconductors or test quantum algorithms. The story of fission is just the ultimate reminder that you can never, ever predict where pure, basic scientific curiosity is going to lead.
And that really leaves us with a pretty cool question to think about. I mean, right now, somewhere in a lab, some researcher is probably staring at a result on a screen that looks impossible, or maybe just plain wrong. And that one little strange result, well, it just might be the seed of a technology that will completely redefine our world in ways we can't even begin to imagine today.
We really hope this look at fission gave you a new way to think about this incredible discovery. Just a reminder that everything we talked about today was drawn from a really detailed and insightful essay on the topic by Jörg Ove Schneppet.
For more deep dives into quantum physics and the history behind it, you should definitely check out schneppat.de. Thanks so much for joining us. Goodbye.
Schneppat.de is a private project by Jörg Ove Schneppet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.